Hey everyone, we have some more applications of derivatives with some genuine fake real life examples. So what we're doing are called minimal path problems. Sometimes they're called the drowning swimmer problems. So for example, suppose you're swimming 200 yards from the beach. In the minimum possible time, you want to get to the place where you left your towel because you're freezing. You can walk on the beach at 110 yards per minute, but can only swim 70 yards per minute. Let x be the distance from the closest point on the beach to where you'll make landfall. I'll come back to that later. What values of x minimizes your total time if your towel is 600 yards down the beach? So basically, you want to get to your towel as fast as possible. So you have a few options. Option number one, you could just swim directly to the beach and then walk the whole way. So option one would be swim, then walk. Just a reminder, so if we're trying to figure out our minimum time, like we know back from like 7th grade science classes that distance is rate times time because you have like yards per minute times minutes giving you the yards. So time is distance divided by rate. So if we do the swim directly to the beach and then walk the rest of the way, so option one, short swim plus walk. So plus long walk, technically. So that's option one. So your time would be 200 yards divided by your swimming rate, which is the 70 yards per minute, plus the 600 yards of walking time divided by your 110 yards per minute. And if you chuck that in your calculator, you get a time of 8.3116 ... minutes. So that's one option. Second option would be to go, okay, I'm just going to swim directly to the towel. I could go like that, makes that noise and everything. So option two is just swim it. So our time would be the distance we're swimming, which Pythagorean theorem, right? 200 squared plus 600 squared square rooted divided by our swim rate of 70 yards per minute. And if you throw that in your calculator, you get a time of 9.035. Dang, that's slower. How disappointing. Maybe all the swimming would warm you up though. So the third option is the what if there's something in between option. So the third option would be to swim some distance down to some distance there and then walk the rest of the way. And that's where this x is coming in. Let x be the distance from the closest point on the beach to where you make landfall. So this is our x right here, which means that your walking distance here would be obviously 600 minus the x. So if you went to 100 yards down the beach, you would walk 500 yards, obviously. So this is our third option is some sort of combo. Where our time will be, it'll still be the swim plus the walk. The walk is the easier part because it'd be the 600 minus x divided by the walk speed. The swim is going to be Pythagorean theorem to get this guy, so 200 squared plus x squared square rooted divided by our swim speed of 70, and then plus the walk, which is 600 minus x divided by our pace of our walking, which is 110. And the domain on this, well, clearly your x could be nothing. That's what we had in option one. Or you could swim the whole way there, where your x is 600. So the two extremes, we've actually tested those out, which is actually a really important step for later. So by doing this extreme situation, it helps you to figure out how to build your formula, and it also provides you some important information that you'll compare our minimum against. Okay, so going to our calculator. If I threw my equation into my y equals, if I go to my table, one thing that's really good to do is put the 0 and the 600 in as a way of, it's like, I know these are right because I'm pretty confident in my logic. Versus there's the, am I confident in my ability to write a formula? A little less so. So if I test my endpoints out, if I put 0 in, I get the 3.117. You see a 7 there because it's a 36 ... that I had written. Remember that you need always 3 decimal places in an answer. It doesn't matter, according to College Board, if you round or you truncate. It's just weird that way. So a 3.11 or a 3.12 would be fine if that was your answer. But we can tell that our formula is working at least so far. If I throw the 600 in, I get 9.0351, and that's what I had before here. So somewhere in between, it's got to be faster, we hope. So I'm just going to pick 300 because it's halfway between, and it is faster. I can use this to help me set my window. I'm going to do my window 0 to 600 for my x's, makes sense, right? And I have my y max at 10. I did my scale of 100. The scales, remember, don't really matter that much. You could even make scales of 0. Okay, so looking at our graph. It's always so slow. Dun, 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 dun. Okay, so I can see there is a spot where it is definitely less than either of my endpoints. And remember, we can find that by going second, trace, the calc menu. We choose minimum, so number 3. And then you can arrow or type, so you're left of that minimum spot. I can even just type the 0 in. For my right bound, I can even type my 600 in. And then for the guess, I don't even need to put a guess in. It'll find it. And it takes me there. So 164.991 ... is where my minimum is. And my minimum is the 7.658. Okay. I want this x value again, so I'm going to quit out of here. Go to my home screen. Right now it's my x. It won't be my x for much longer as if I hit trace or do anything graphing. So I'm going to store it, which is the STO button immediately above your on button. And then alpha, which is right below the second, and then I'm going to call it A. That way I can use it again later. Okay. So we have our answer. There's more to it, though. There's always more to it. Whenever you have story problems, you kind of need to show you know what you're talking about. So we need to do a couple things. One thing you need to do is to write a sentence to explain yourself, basically. And notice that I haven't actually found the derivative here, and that's okay. I don't really need to. What I will do instead is I will turn on my NDeriv. I'm not going to graph this. I'm actually just going to go to my table. I don't really care about the 0 or the 600 anymore. I do care about the A that I had from before, my stored x value. So I can see here's my time, the 7.658. My first derivative equals 0, so that's good. Shows, hey, this is flat here. And then my second derivative, although this number is very, very small, since you have that times 10 to the negative 5th, it is positive. That positive value, remember, tells me if I have a positive second derivative, I have concave up. So if you're flat and concave up, you have a minimum. So even though I haven't algebraically found the derivative, I just did it with the calculator, that's totally fine on these problems because these are calculator active problems anyway. You don't have to do the hard job. And it's efficient or lazy, I don't know. So your last piece you need to do is to write a sentence, which I actually did this in advance to speed things up. So it's sometimes really hard to write your sentence in a way that makes it make sense. So this is what I wrote. Minimum time of 7.6585 ... minutes if x is 164.991 yards. And then here's what I did to make it so it's really clear, because that 165, I'm going to round for the sake of speaking. It's hard to know if that 165 is here or the walking distance. So I wrote this extra sentence of swim to the spot 435.008 yards from the towel, which is the 600 minus my x. And then I also said this is faster than either endpoint. And so this would be all on one sheet of paper, not on a separate one, obviously. So you can see that my endpoint is there. I know it's a minimum because t prime equals 0 and t, oops, I forgot a prime, t double prime is greater than 0. So I have that concave up in a minimum when x is 164.991 yards. So this few sentences makes it so I've clearly shown that I know what I'm talking about, and that's what you need to do. So even though I'm not algebraically finding my first derivative, or, ooh, gosh, even worse, finding the second derivative of this guy, I'm clearly showing that I know what I'm talking about and have been very careful and thorough with it. So you do need those endpoints so you can compare, because remember that endpoints are critical points. Your minimum can happen on an endpoint or on where your derivative is 0, so you do have to check both. So this is our introduction to minimal path problems, aka drowning swimming problems. And I know this is super realistic because, you know, if you're swimming and you're in the water and you're freezing, you're clearly going to do calculus.